Cool. Started the recording. Did anybody have any general thoughts about the chapter? Any questions, concerns, things you thought were cool?
Rust's kind of weird.
How so?
Just like the memory model. I don't think I've seen anywhere else.
I think it exists in other languages as well. I'm not entirely sure what they are, but I don't think it's the first to do it.
Probably not. Time to
But yeah, it
research.
is pretty interesting. Okay, so a few of them. I'll drop this link into chat. So a few of them that I found from this beautiful Reddit thread. Dion ML kit, carp linear ML. Oh, maybe these are linear types. Okay, maybe I was wrong about that. Cancel. Oh well. Well, if you find anything, let me know. Maybe Rust is the first to do it. Anyone else have any thoughts? Okay. Then let's get into it. So I think I mentioned, but this will be most likely 2 parts, or multiple parts at least, since we really need to dig into memory to understand memory safety as a whole. Kind of need to know the why we're doing it instead of just Russ says we have to do it, so we must. Okay, but just in general, to start out and talking about the memory management model being weird is pretty good because that's the first thing I'm going to talk about. So, can everyone see my screen, by the way? Oh, no one can see my screen. I apologize for that.
No. Okay.
Well, at least I was just showing that Reddit thread I already put in chat. But here is Excalibur. Can you see that?
Ooh. Galadraw.
Yay, Excalibur. I get to draw things very slowly for everyone.
I love Excalibur.
Yeah, so getting into those memory models, the 2 typical ones we see are garbage collection and then as well manual memory management. So anyone have any pros and cons of either one of these? What are they and why would you pick one or the other?
Well, garbage collection is certainly more convenient for the programmer in most cases, since you don't have to obviously manually manage the memory. The garbage collection collector does it for you.
Does anyone know how to do bullet points on here? I've seen someone do it before.
Just do little hyphen.
Oh, cool. Thank you. So it's convenient. That was your point?
Yeah. And those who have your security concerns, it's a big for manually memory managed languages.
Sorry, you're cutting out for me.
About like buffer overflows. Oh, sorry. I think I can you? Hello?
Hello?
Hmm. Hello?
Hello?
Can you hear me?
Yes, now I can.
Okay. I don't know what happened. My mic wasn't picking up for some reason. I don't know what you caught from what I said before, but
I heard something about
there are a lot
security,
more.
but I
Yeah,
didn't.
there's
There's
some
a lot of
security
cutout.
concerns. Like you can easily have buffer overflows and double freeze and stuff like that in manually memory managed languages. So garbage collection sort of avoids that.
I'll say prevents common memory bugs, or we can say the buzzword memory safety. It's memory safe, convenient and memory safe. So then the opposite's true the other way around. Then so
As like a con, yeah.
harder to learn and not memory safe. You can do those or double freeze, like you mentioned. So then what about the other way around? Are there any pros of manual memory management versus garbage collection?
Yeah, for manual memory management, can be more performant because you're just not waiting for garbage collector to free up memory, deallocate memory. You do it yourself, and so theoretically, you always know what data is where and how to optimize your service or software.
Okay, so you have the potential to optimize your memory usage.
Yeah.
Okay. Anyone else have anything else? I'll put not as customizable for garbage collection, since you can definitely change some things, but you can't manually free whenever you'd like or allocate memory. There's one other thing that we went over in the... Oh, sorry, go ahead.
Oh yeah, so I think I just answered my own question. Since it's your
Okay.
garbage collecting, so memory like JavaScript garbage collecting.
Yeah.
There is not a possibility for a memory leak unless you directly manipulate the data, right?
It's still pretty easy to cause memory leaks in JavaScript, I would say. Like, for example, let's say we do an event listener on a DOM element, and then you remove that DOM element from the page, but you don't delete the event listener. That's a pretty common circumstance you'll run into. So if you forget to do that, then memory leak.
Gotcha. Yeah, that makes sense. Thank you.
Yeah, so that's a good point to bring up, though, since garbage collection and memory management, or even the Rust way of doing things, don't prevent you from having memory leaks. It's just preventing specific kinds of memory bugs.
Yeah, it may be good to find what exactly a memory leak is, although we may get into it later.
Yeah.
I don't know.
I think it's good to go over now. A memory leak is just, well, I'll let someone else answer, actually. Does anyone know what a memory leak is? Good call out, by the way. Someone sent a video of a dam over for having a leak in it, and that was unfortunately not the answer I was looking for.
But isn't it though?
Maybe.
I could look up on Wikipedia. I don't know, like the technical term. Maybe not at that scale.
Okay, I'll go through then. So memory leak is purely just unused memory that does not get recollected by your garbage collector. If you're using a garbage collector, or in the case of manual memory management, maybe you made a mistake there. So in our case, we have a function for our event listener that's never going to be called, as well as that event listener, because that DOM element doesn't exist anymore. Yeah, okay. So one other thing that we did not go over, but we did go over in the intro chapter, is garbage collection gives us lots of latency spikes because it's not as customizable. So you could collect a lot all at once. So with our manual memory management, you just get rid of it once you're done with it. But with garbage collection, it'll happen on an interval. And whenever that happens, your code's going to have to slow down for that. If you have a single threaded language or environment, it'll just be your program has to wait for the garbage collector to happen. But yeah. So here's a Figma blog on this, actually. I couldn't find that original article, but looking here.
Figma blog.
Yeah.
Figma has blogs?
Yeah.
What?
Looking at
Sorry,
it right now.
that was crazy to me. But go ahead, sorry. I was like, what?
Indeed. So here, they swapped their server to Rust. I don't remember from what. Oh, it was written in TypeScript. So perfect. Single-threaded TypeScript. So over time, they swapped over to that. And you can see these spikes are a lot more significant for memory than we have here. Network traffic's going to be around the same. Can't really do much about that. And then the CPU and time to serve a file, it's very flat. There's a little spike here, but you could see with the TypeScript version, as it's being rolled out, you get less and less of those big spikes.
Oh, wow.
Oh, they have pros and cons here too. Cons, lifetimes are confusing. Yes, agree. Yeah, so the peak worst case is 82 second for save time. And then file serve time. Yeah.
Oh, that is crazy reduction.
And then when we were looking at that older document, it was just kind of up and down. And then we saw the JVM startup took like a ridiculous amount of time. So there's no overhead there either, but that's just getting into Rust at that point. Yeah, any questions there?
When did they make the switch over? When did they restructure their architecture?
Unsure. May 2nd,
Yeah.
2018 is when this article is written. So
Oh, wow.
we have, April of 2018, it seems.
Oh, wow, that is amazing. That was my only question.
Yeah. Oh, yeah, I can drop this article in chat as well, in case
Oh,
anyone's
thank you.
interested. So then why would we want to use a garbage collected language versus a manually memory managed language? Is there any reason or any time we would want to use one over the other?
Assume like use case. If you
Yeah.
don't need like super performant application, why use manual memory management?
Sometimes it's impossible. Can you hear me?
I
Cutting
think
out
so.
again.
Cutting out a little bit, but yeah.
Okay. It's impossible to use a managed language if you're programming on something like an embedded system. That would only support something like C assembly.
Yeah, that's a good one too. I think I heard memory managed, or no, an embedded system.
Yeah.
Yeah. Yeah, so a lot of performance. And then another use case, potentially something where we really care about the timing when something's happening, because we can't really be sure when the garbage collection is going to happen. So out of these pros and cons, where does Rust fall in here? Because it's not either one of these.
Falls in the middle.
How so?
Well, because REST isn't either. I believe it takes from both paradigms. For example, ownership, Chavez ownership. So ownership essentially takes care of memory for you, but you're able to access memory directly by, for example, using the owner and pointing it to where you want it, which variables you want to have ownership at a certain period of time. And also, you're referencing as well. So if you don't want to have, I'm just trying to think of, it's been a while since I read the chapter. So if you don't want to necessarily have ownership of a specific piece of data at the moment, but you want to allocate it to memory, you could use referencing. And so it could do it for you automatically, but also you can control it. Is that right?
I think we have a little bit of a disconnect on what manual memory management means. So for that, we mean specifically saying, I want to allocate this many bytes of memory, or saying, I want to free this memory from the heap. And specifically, like safe Rust as well. So in Rust, you can't do either one of those things. So Rust does not let you manually manage your memory. That's hard to say. But yeah, ownership is the way Rust manages memory. So I guess that should be here.
Are there any caveats for that regarding unsafe?
Oh yeah, you
Rest?
can call C in your unsafe code
Okay.
or directly change memory, but we're not gonna talk about that for now. We'll get into it in chapter
Regular
19, I'm pretty sure. Yeah, regular Rust and safe
Ah.
Rust. You're not allowed to manage your memory manually.
Okay. And only in unsafe Rust you can manage memory.
Yep, you can call some C functions and just do it if you really want to, but at that
Gotcha.
point, you're not really writing Rust. You might need to for some specific optimizations, so it's not like you should never do anything unsafe, but for right now, I don't think any of us will need to do any of that.
Hopefully not.
Yeah. So what are the pros and cons of the ownership model?
No latency spikes. Woo.
Yeah, that's a good one.
No double freeze. Woo.
I'll just put memory safe again. Yep, also memory safe.
Okay.
I'm not going to write every single memory bug. Any cons?
I'm gonna say it's more complicated to understand the memory model than in either the garbage collection or manual memory management case, I think.
It can
Since
be.
in the garbage
go ahead.
collection, you don't really have to think about it too much. But in the manual, it's still typically you declare a section of memory to use and then you free it. And that's basically all there is. But to deal with Rust's ownership model, you have to do some interesting things to make it work.
I can see that, yeah. I personally find it easier to use Rust ownership model, but if you're familiar with manual memory management, then that is 100%. I'll expand that for our complicated to understand, but also you have less freedom in general.
Yeah.
Compilation times can be longer, I'm assuming, because Rust does a lot of checks before
Yeah, exactly.
compilation.
That's a good one. We'll get into that a little bit later as well. A little bit more into it.
One benefit, which I'm not 100% sure is just this, but having the ownership model probably helps with compile time messages and like information that the compiler can give you. That's why Rust has such verbose warning messages and errors, unlike something like C.
Okay, so because we have less freedom and it's more strict, we have some more specific rules to follow as opposed to C, which
Right.
might just say or break during runtime, let's say.
Right. Yeah, like because you have to define more stuff, like there's more rules, more stuff can be inferred by the compiler, which is useful.
I, I also feel like you are more aware of when it's memory is released because in like, for example, if in a garbage collection you have no control over, you just don't know when it's getting collected. But in Rust, based on the rules, you have an idea when it's getting released, memory is released.
Yeah, that's a good one too.
Yeah, the scopes are very strict, and the compiler will yell at you if you ignore it.
Yeah.
Yeah, I think that's a pro of manual memory management, or maybe it's not a pro. It could be a pro in Rust case and a con, or a pro or con for depending on who you're asking and when you're talking about it. I think that's a debatable one. Whether it's a pro or con, that is.
Yeah, it
Nice.
probably depends.
Any other ones?
Mm.
I'm not looking for anything in specific, just wondering because we had some good ones I didn't think of.
Ferris. That's a pro.
True story. There we go. Perfect.
Yeah, Ferris.
Okay, so I think we're pretty set here. But beyond that, with the freedom, we will definitely get into it. But since we're in Excalibur, we may as well. So I've seen this before with, we can have this circle, which is memory safe programs. And then within, we can have another circle of, wow, I do not know how to use Excalibur. Let's make this blue.
I have a clarification question
Yeah, go for it.
regarding the term memory safe, and I guess just memory safety in general. Does that refer like to a specific set of memory bugs? Because like you were saying, memory leaks are kind of different. Is it like a memory safe program mean you can't have, is it just like invalid memory access? Is that sort of a way to think of it? Or is it sort of not that strict of a definition?
It is a pretty strict definition, and that is a great question. I do indeed have a what even is memory safety bullet point here. So pretty much memory safety is the absence of undefined behavior, which is another spooky thing. So undefined behavior is just anything that's not in the language specification. So for example, like you mentioned, we're reading some freed memory by chance or somehow, or I don't know, we just read freed memory. So anything could be there, or we read some non-allocated memory. So we read outside of the bounds of an array. We don't know what's there. We're not supposed to be reading there. So what happens if we have an if statement, let's say, and in that value, that piece of memory, so in Rust, false is 0 and true is 1. So a Boolean can only be those two values. So what happens when it's 948?
The Boolean?
Yeah, what happens if a Boolean is 948?
With you an error.
Well, if it's Rust, it wouldn't let you do it.
Let's say Rust
It
doesn't
could
have these
overflow,
rules.
yeah.
What if it's 948? We have if 948.
Well, it depends. Yeah, I'm guessing it's going to be undefined behavior.
Yep,
Basically.
exactly. Undefined behavior. It really depends what happens. It's not defined by the language specification. They didn't plan for a Boolean being 948. They're not going to check during runtime if this number is 948 because we've said this number is 948. The compiler has, it's not, it's a Boolean. It's either 0 or 1. We've confirmed this information at compile time. And you're not allowed to do something that makes that not true. So, yeah. I think that's a good thread to go down as well. So, what is something that could happen?
It'll crash your program. Or could.
Let's say consequences of.
I mean, if the behavior is undefined, it could literally do anything. Pretty much.
So you say crash the
Right.
program. That's a good one. What's another thing that falls under anything? Why should we care?
Technological singularity. Yeah, that's the second point. Yeah.
What did you say?
Incorrect.
Eric said technological singularity as one of the
I'm ready
concepts.
for
That
the
is true. That could
singularity.
happen.
And,
Anything could happen.
I don't know what that means, but we'll write it down.
I think he's talking about like
the AI.
robot.
I'm ready.
Singularity.
That's true. We could decide to take over.
Mismanaged allocation.
And what could that do? Or what does that mean for us?
Oh, if you're expecting like a 1 or 0 for a Boolean and a function is trying to take in that value or some other piece of code is trying to reference that value, it will get the incorrect value and not execute correctly. And so you'll get the wrong output.
Yeah, that's a good one too. Just gives you the wrong answer. And we don't like when functions do that.
Yeah. Eric says overriding or corrupting data.
Yeah, good one.
It's probably a security vulnerability, although it depends if it's like part of input. But if the behavior is undefined, I wonder how useful that would be.
Ooh, it's useful. Potentially.
Right, but it's like if the behavior is undefined, is the behavior consistently undefined? Like if you give a program with undefined behavior like to some function, right? So it's like the input to your Boolean is 962 every time. It's not going to do the same thing every time because the behavior is undefined, right? It could do something different each time you try to run it with that same input.
Potentially. Or it could
Am
do
I
the
thinking
same
of-
thing every time. Like,
Yeah.
there's a lot of cases where it's very predictable what will happen for this specific
It
version,
depends
but
on
it depends.
Yeah. There's so many ways to trigger undefined behavior in like C. So it just depends the mechanism probably.
Yeah, if you are a hacker and you're aware of some undefined behavior that works similarly, so the point of, or a part of undefined behavior, so your language could react similarly every time, or it could react differently for every version, or every different way you compiled it, maybe. So it's possible that it's very predictable and you know how to do it. Or it's possible that maybe it's hard to exploit. But I do have an example, a concrete example of this. to get to, which I will also put in chat. So here is a cool video that came out recently, and I thought it was very on topic. So in this case, we use unsafe behavior. Well, not we, this person does, or not unsafe, undefined behavior.
Mario Kart Wii. That's crazy. How did this even happen?
They use a security vulnerability to cause undefined behavior. So for the servers for Mario Kart Wii, or at least the security handshake, they use an exploit to get past that. But the part we care about here is they cause a buffer overflow because the code for this specific version, or for a few specific versions of Mario Kart Wii, does not check, or the networking code does not check to see if they overflow the buffer. So let's say we have 256 bytes were allowed. I'm not sure if that's what was allowed, but you could write, let's say 900 bytes. And at that point, what happens, since specifically in this case it's predictable because the actual area where that buffer is held in memory is the same, they can predictably find memory values that they want to edit, and they can change those values. So that's how the current Mario Kart Wii servers do things. And then it's also, so if you go on someone else's Mario Kart Wii server, they can run whatever code they want on yours, on your Wii. So be careful about that. But you could also use it to change different things, like they change the speed of the game, do various things. But yeah, they just write past that point in memory. That makes sense?
Yeah, it does. It's just shocking me. Sorry, go ahead.
So in this, I haven't watched the video yet, but in this case, is it actually referring to undefined behavior, or is it just a security vulnerability from like a buffer overflow, like a memory, like unsafe memory access or something?
Both. Undefined behavior. So a buffer overflow is a security exploit, and also undefined behavior. So the language specification did not define what happens when you write over a buffer. So they're writing to bytes they should not write to.
The same or not?
Yeah, they're not mutually exclusive things.
Whoa. Okay.
So that brings up another good thing. Let's find it. Yeah, so looking here, so here's a layout of memory. It's an example of how it could be laid out. So if you've heard of a stack overflow, all that is your stack. You've pushed too many things to the stack, so you could do recursion and go over. But after that point, once you've exhausted your stack, if your CPU doesn't check, or if your program doesn't check, then at that point you start overwriting more and more. So you can go past this heap data, go over here, write over your program itself, and then that's obviously some undefined behavior. Nothing really says what happens when you start overwriting your own code in memory. But yeah, related to what we're going to talk about. So we have here text, which is the The instructions are actual code, and then the stack and the heap right here. But yeah, to get back to here, any questions so far?
I'm good. You've been doing a great job explaining to me.
Perfect. Okay. We have one more thing that I'm looking for here for consequences, but it might not sound like a consequence. Nothing. So yeah, any one of these things, these aren't mutually exclusive. So nothing could happen sometimes. And then other times when you put just the right input in here, you cause a security vulnerability. So we've been over this before with Rust. Let's see here. Yeah. So we could do this again. So let x, if false, let's assume this is like an input. You input some data on your server. We're going to do x equals 4. And at this point, we're going to print this value. So this doesn't compile because of that. So it could be as simple as this. If Rust allowed this to compile, we could potentially print something that doesn't exist. And what happens then? Undefined behavior.
Yeah.
Hold on a second, sorry. Sorry, my dog wanted to see me, and my mom was sad that they couldn't come and see me. So I had to pet them real quick. Very important.
You're good.
Yeah. And since we talked about these if statements before, I found out that Rust just doesn't even try to check to see if this will run. It just assumes it doesn't, which is the much safer option. Which is why if we do something like this, this is a memory safe program. It'll work perfectly fine, but Rust doesn't allow it. Taking us back to here where Rust doesn't allow that program, even though it would be perfectly fine if it ran. Any questions here? Nice. And, oh, okay, some other things that could happen. They're pretty hard to debug potentially, because we could have that nothing case, and then maybe it's not even on purpose, but you write some code and then it does something unsafe. Like it writes past that buffer that one time. So like in the Wii's case, it works perfectly fine unless someone writes too many packets or too much data. They write too much data to your Wii and then it breaks something. So it works fine most of the time. And then you have to figure out, why does that happen? It broke only this one time, and who knows why. Or maybe it breaks and gives you a slightly incorrect answer, and you don't know why. So they can be pretty tough to figure out. And they're pretty easy to do if you're not aware. And then here, we have our extra credit. of everything considered undefined. But yep, that's at some extra credit, so feel free to go through. There's also a whole unsafe Rust book to read called the Rustnomicon. We're not gonna read that either for now. I don't think it'll. Yeah, for now, makes it sound like we will, but I don't think we'll get into it. Yeah. So now let's get into some more memory stuff. So we've gone over a little bit how we can do a Stack Overflow, but less so how does this work in general. And then also the stack is an actual stack data structure, but the heap is more like a pool of data.
It's a heap.
Mm-hmm.
Although I guess it's not like a heap data structure, is it? It's
Nope.
just called that.
It's just called that.
More like a traditional heap. Like
Yeah.
of apples.
Yep, like a heap of laundry. Like we have the stack. We either push to the stack or we pop from the stack. It goes one way. There's only one place you can remove or add to. But with a heap, you can just pull something right out of the middle, which leads to some challenges. And then just in general, ownership and the Rust memory model tends to be, or is just, how do we manage heap memory and pointers? So if we have the stack, we have the stack holds stack frames. Does anybody know what that is?
You said stack hold stack what?
A stack frame?
Oh, stack frame. I do not know that.
Okay. So a stack frame is just a mapping of your variables to a scope. And we're going to look at JavaScript for this because I couldn't find an amazing or any way to see a nice visualization for Rust. But hopefully we're all familiar with JavaScript, but I will explain. So in this case, functions in JavaScript are objects. And since they're objects, in JavaScript, those are modifiable by default. So we don't know its size at runtime. So it must go on the heap. And then everything else, which we do know, like these numbers, every single number is equivalent to an F64 in Rust. So we know how big they are, so they can go on the stack. Okay, that started from the end. Okay, so starting here, we have those objects in the global frame. And for here, we have X and Y, which are both undefined. So here we have X. We're pushing this on to the stack. And it's kind of interesting that it's upside down like this, but it is exactly the data structure. So we push onto the stack and pop off the stack. So starting here, we have this frame for main. We know 5 is 5 immediately, but once we get to Y, we have to add 6 to X. Notice here that this X is a copy of this X. It's not a reference to it. We just make a copy. So changing this one doesn't do anything to this X. So we have 3 more in this X. So we're going to figure out what is 3 more. And see, we're pushing onto our stack, and we have to resolve this stack frame before moving on to these other ones. So add 3 has x, which is 5, and a return value of 8. And then once we have this, we hit the end of the scope. We return out of the function. So once we do that, we know the value of 3 more. And then 6 more copies the value of x at the time. Well, actually, it does 3 more, which is 8. And then we go through that again. We add 3, and we're at 6 more, which is 11. And we return that to main. And that is now 11. And then both of these go out of scope once we finish main, and that stack frame is popped. Any questions there? I see someone typing. Yeah, frame is a scope. So ultimately, I don't believe we care. Like, let's see. If we add a new scope in here, I think it would be on a different frame, but let's see. Let's actually throw this here for the sake of time. Yeah, so we have another Y in here. Oh, well, I guess that's in a different block, but it's fine. Yeah, so see here how we have another block within here. And then once this block is over, that's no longer in the frame. So you could think of it like popping this from the stack and pushing a new main to the stack. Or you could just leave it there, but it's pretty much an implementation detail. But the important part here is that these specifically are mapped to functions. So at the end of the scope, all of these values are deallocated, and then everything here has a known size, so we can put it onto our stack. And then a different example, the heap works differently. So we already had these objects on the heap at the start, but moving here, once we allocate x here, x is a pointer to this object here, which is on the heap. We don't know how big it is. We could change the value in here to something different, an unsized something, like maybe we add a string in here, we add an array in here, we add another object in here, we add more keys. We don't know. You could do anything you want. You could delete a key. So if we added a key, we'd have to deallocate this memory and allocate somewhere else. And then here we have y equal to x. So they're both pointers to this object at this time. And we can add 3 to that object. And even though we're passing y, it's going to change both of them because they're just the same pointer. And then looking here as well, x is a third pointer to this object. And then a question here for the audience. In Rust, would we be allowed to have 3 pointers to the same memory in the heap?
Yes, as long as it's immutable.
Yeah, exactly. So in this specific case, we're modifying the value we push into y, and we already have a second reference here. So if we weren't modifying it, it would be okay. We can try it out though. I guess it depends on the semantics, but here in JavaScript, all of these are mutable, so this is not allowed. Or is it? Who knows?
Well, if it was in Rust, though, which one's changing? Add 3 to the y is changing.
We're adding 3 to y.
It's weird because you can't, because the syntax doesn't match up, so you can't really.
Well, yeah, at this point,
since JavaScript treats everything as mutable, but like you could write this in Rust and make it work, but you'd have to pass like the y as a reference or something in the function. Yeah, 3, I think.
I think this would actually be perfectly valid Rust, because we take x, and then
it
x
keeps moving.
Y is now the owner of x. So it would change a little bit. You're allowed to do that. So x would be then a pointer to, or just nothing. So as long as we're not using x, it's fine. And then at y, we could pass a reference, or we could give ownership, and we just add 3. So that's fine here. And then we don't use it again. So I think it would be fine. And it's a memory safe program because JavaScript, but assuming we're doing pointers, I think it would be memory safe as well. Tricky.
This is where I trust the Rust compiler to yell at me if I messed up, and then I do what it tells me to do.
We could write this in Rust and see if it works.
Do it.
Let's do it. Okay. So we have x, which is a struct. Which has a value which is a number. Which we can just say, I don't think we can say 5. No, we can't. And this is not TypeScript, so we can't do that. So we can make hi here, which has a val of 5. I'm going to close this real quick. And then at this point, this is fine. And we can say let y equals x. So it's moved here. And we can make add 3. Which takes in x, which in this point is our high struct. And we don't return anything. And all we do here is x.val plus equals 3. It's not mutable at this point, so we can't do anything. So what happens if we add 3 and pass in x?
Y.
It should say no because it's moved. And if we pass in y, it's fine.
Easy peasy. Cool.
Yep, so it is totally valid in Rust. Just the semantics are a little bit different because we would not be allowed to use x. But we could definitely use x if we were in JavaScript. Any questions about that while we're here? Okay, back to stack and heap. So yeah, we have 3 references to this one value, which is okay here. and then we're going to edit that one value. They're all pointers to an object that has a value of 8. And then what happens here in Rust? Specifically talking about, is this memory deallocated at this point if it were Rust, or would it stay?
Well, it would be moved. It deallocated though. Right, because it's when it's passed in.
Well, let's
The
say
data
once we
is
hit the end
moved.
of the scope of add 3, so we're at line 10, is
Okay.
this object, or let's say
Then, yeah,
if
it
this
should be
struct deallocated,
it
or
should be dropped since.
let's say heap
Oh,
allocated
wait.
memory, because yeah, let's just say it's like a string or something, because that would be on the heap.
I would say it's dropped because you've passed it in, which has then moved it into the function, and then the function has gone out of scope once you return. And so I think it should have dropped it.
Yeah, I agree.
And-
Unless you pass by reference, yeah, this is not
Yeah.
going to work.
Yeah, because then it won't move it.
Okay. Any differing opinions here?
Any dissent in the ranks?
Okay, I don't hear anything. So yeah, I agree with that. Once X goes out of scope, it's then dropped. So then, since it was the owner of that data, dropped means deallocated. I'll also say free. They're all common terms you'll hear. So at this point, X is dropped because it hits the end of the scope. And then since it's the owner of this value, this heap memory is now deallocated. And then once we're here, Z is a different object with a value of 8, and it points to a different object. Yep, does that all make sense? Any questions? Okay, sounds good. So the thing here to note is everything in the stack, all of those variables, only last for one function, for one scope. So the heap allocated data is allowed to outlive your function. So in the case that we did pass a reference, then the heap value would still exist at this point. But once we drop Y, then that will be deallocated. But it only matters for the owner, because in the case that we dropped it for every reference or every value that points to that data, then X and Y would both be dropped or both deallocate that heap memory. And we would try to deallocate some memory that we already deallocated, and something else could be there at the time, which would be unfortunate for us, because then we would have some more undefined behavior if we try to use that, read that memory. Yeah, so I didn't end up drawing anything, but any questions before I draw some stack and heap memory?
I'm good to go.
Perfect, okay. So we're looking at the heap. We're looking at the stack, let's say first. we're just throwing everything on here. So we have our data, all the variables in this first thing. We make a function call. Now there's more up here. And then we finish this function call, go back down here, pop off the stack. It's all very linear. But if we do something different, and this will definitely be just an implementation detail of how we do it, but I'm just going to go through it. So let's say we allocate a string. We don't know how long that will be, so we have to throw it in here. We don't know how long that'll be in runtime, so we throw it right here, and that works. And then afterwards, we find the next hunk of memory that can take in something else. So maybe we have a vector here, and then we throw in a longer vector and something else. But then we reach the end of our scope. We don't need this string anymore, so we deallocate it. And then let's say we have this string here, and we decide to resize it. We're going to add some letters to this string. So here we have to deallocate this memory, and then write this longer string somewhere else. So maybe we find here, and then what if we take this vector and make it longer? So ignoring the fact that this is one big square, we could, let's say that this is also part of our vector. So we need a big continuous piece of memory that fits all of this in here. And we can't do it here. We could deallocate this, and then this is the start of our memory, and this is the end, and that works. And then eventually, maybe we write some smaller strings in here. So we have this, 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 and this. And then we fill out everything. And then we delete something and try to write a vector in here that's this length. So at this point, maybe we have enough space for this, but it doesn't fit anywhere. So that's just to say we don't really have to take anything out of order, or we don't have to take things out of order, or sorry, we don't have to take things in order when we deallocate memory. And then as well, if we increase the size of something, we have to deallocate and reallocate in another space. So adding to a number doesn't really take much because we just change some of those bits and it's the same size memory-wise. But if we do something here with a string or a vector, those can change size. So it's much harder. We have to find a space where that fits instead of just a stack, which is literally just incrementing a pointer. This is, the stack is essentially an array. So we could say like, here's 0, here's index 100. If you want to push to the stack, you write to this memory at 0, and then next you increment the pointer. Now you write to the memory at index 1, etc. If you want to pop off the stack, you decrement. So it's much simpler than all of this, and we have some pretty bad holes in our memory. So maybe that means to fit that value in there, we just compact our memory like this, and then now it does fit. So all of those things are potentials when you write or you allocate memory to the heap, which is the reason why we don't just copy everything. So if we have a number, we're just going to copy it because it's not as bad. But if we have something heap allocated, we're not going to copy it implicitly. Does that make sense?
So for like larger data structures like arrays or vectors, is it actually a concern to copy the whole thing because of the memory management? Like, will it try like that? I thought you used like references instead of like copying large data structures like that, just because it would be a waste of resources. Does it actually try to reallocate the whole thing onto the heap? Because wouldn't it just be copying it into the stack? I guess is my question.
Oh, okay.
Use it.
So let's say this is our stack here. Just like in that example, it's just a pointer because we know the pointer's size, so we can easily put it on our stack. So the stack has a pointer to these objects or to the heap memory. So if you have something on the stack and you have another reference, it's just another pointer. Does that make sense?
So, like when you have data on the heap,
Yeah,
that you want to access, like let's say it's a vector of things or something, you're not going to copy it because you're going to be using a pointer, right? So
I
you
think
don't
you're
need
cutting
to.
out.
Oh, sorry. Is it?
I heard vector of strings.
So let me think. So like we're not avoiding copying because it would trigger more heap allocations, right? We're avoiding copying because we would have to copy the entire data structure on like to the stack, access it. Instead, we just use a pointer and then we have that to the beginning of our vector. You can just access the whole thing while it's still in heap, right?
We could heap allocate anything we want. We could heap allocate numbers if we want to. We could heap allocate arrays if we want to. So it's not a matter of that necessarily. Just it's a trade-off. So it's easier to put things on the stack, and it's fine. We've decided it's okay to just copy it implicitly because it's not that bad of a runtime trade-off instead of taking a reference to our number. But that might be the case. Like we had an array of 10 million elements. We might want a reference to that instead of copying it. But yeah, it's just much more costly to make heap allocations and stack allocations. So let's say in this case, instead of, let's put it to something more specific. So we have
Like, yeah, I get that it's cheaper to do the stack allocations. I think my main question was because I heard you say that we do the copying to avoid doing like more heap allocation, and I thought like that wasn't the case.
oh, okay.
I
Okay,
don't know
okay,
if I
okay.
misheard you or not, but
So if we copy a number, we don't have to do heap allocation. But if we copy a
right.
dynamic collection, like a string, we do have to make another heap allocation. So that's the reason why Rust chooses to do references to those things, or not implicitly copy them, at least. Like we have 3 small strings here, we have to find places for all 3 of them. But 3
So is a
numbers.
copy operation from the stack to the heap, or vice versa? I was understanding it to be not that when I read about it in the chapter.
a copy operations from the stack to the heap. If you decide to, okay. So let's say we have high to string, or yeah, we have high here. And we have this cool function called move, which takes in, I guess we can just say a string. It takes in a string. And all it does is move that value. Did I do something weird here? Oh, it's move. Oh yeah, move is already a thing. Move string.
Your keyword.
Yep, it is a keyword. And it does exactly what you think it does. So we have these things here. I forgot where I was going with this actually. Oh, no, I remember now. So, like, getting into this, we have move string, and we can't do this because it's moved here. But if we clone it, then at this point, we are making 2 copies of this value, and both of them are heap allocated. So there's 2 highs. But if we do 5, in this case, it's implicitly copied.
So, yeah, okay. I forgot about that part. So, because it's a dynamic data structure and not something like that we know at compile time, like for the integers, every reference to it, like, or every instance of it, I guess, has to be stored on the heap. So it's always going to be on the heap. So if you make a copy of it, you also have to store that copy in the heap.
Yeah, exactly.
Yeah, that was, yeah. I was thinking you could store like a copy of it in the stack, like momentarily right before like you went out of scope. But since it's a dynamic data structure, you can't do that.
Yep, you're only storing a pointer and then potentially a copy of that pointer instead.
Right. Okay, cool.
Okay.
Oh, gotcha. So it only goes on the stack because it's a known known size of the data structure.
Exactly.
Yeah, for like integers and stuff. Yeah. Okay. Thank you for clearing that up.
Oh man,
I thought I was going crazy.
Yeah, me too. I was trying to follow along. Oh man, thank you. This makes so much more sense. Okay.
Yeah, glad to help.
Yeah. So like to just reiterate, so string and vec are growable, which means they are not defined with the size, and because of that, they go on a heap. And if we have like a signed integer 32 value, which is, and let's see, just be a single number like 5, that's automatically I32, right?
Yeah.
Okay, so that would go on the stack. Gotcha.
Yeah, exactly.
Cool.
So if you do anything that just does that, like even if we have an array, so we do a lot of these, a million, we have a million. This is totally fine and it copies, but since this isn't, this is the wrong type now, because I decided not to overcomplicate things with the generics, but I have to. Oh no.
Oh, that's
1, 2, 3,
just
4,
the
5, 6.
Okay. That's a 0 filled.
Oh, this is wrong. It's I32
array. Is that a 0 filled array with a million values of 0?
Yeah.
Okay.
So this is copyable. It implements copy because all of its values implement copy. We're getting into traits on accident. Oh no. But yeah, these are all copyable. They're a known size because this array is just a million zeros. But in the case we don't want to do that, like maybe we don't actually want to do that and copy it over, you could still do a reference to it or put it in a box. Either one. And then that way you are not copying a million values, which is a little tough.
Make
on
it a
performance.
billion. That way you'd have a stack the size of a gigabyte.
I wonder if we can do a billion. I think you can. It's probably 32. It's a U size. So
yeah,
could,
it would Wait, is it U? Because
Kind.
would be 2 billion, I think.
It's a
2
U size
point
because
something
array
billion.
indices are all positive, or they're all non-negative.
Okay.
So yeah, that's just
Well,
fine.
right, but an I-32 would be like negative 2 something billion to positive 2
Oh,
something billion.
okay. Array lengths
And, like-
are bound to a U size, but
they're U size.
I32s,
Okay.
we're allowed to put whatever we want in here.
Yeah.
We could make this an I-128 and it's still fine. We know exactly how big it is.
Is a U size also 32 bits? Or is
U
it, like,
size depends on your
architecture-based?
architecture. It's 32 bits or
Okay.
64 bits, depending.
Neat.
Yeah.
Not that you'd ever need to use a full 64
You might.
bit number. Well, there's no
I don't
way.
know.
If you're addressing, if it's like a single byte per element, 2 to the 64 is like more than like the possible amount of memory you could have. Right? 2 to the 64.
Yeah. I mean, I did the math for JavaScript, and
Yeah,
we
there's no
mentioned they're
way.
F64s. So if you had an array with JavaScript, the limit is the 32-bit integer limit again. So if we did that, it would be, I don't remember what it was anymore, but it was somewhere in the hundreds of gigabytes of of memory. So you're probably not going to get there.
Oh wow.
Yeah, I mean the 32-bit, like you could have like 4 billion. That'd be like 4 some gigabytes if you had just like a single byte per element, and then like 4 billion elements like in the whole thing. You'd have like 4 gigabytes if you like use the entire range of the 32-bit integer, or the unsigned rather, because it would start at 0 and. Ooh, what's the max? Must be in a string literal.
I forget. I can just log it every time instead of questioning. Whatever that number is. I think that's the same as 30 or 64-bit.
I don't think so. 64 bits way bigger.
64. And let's do U32 for fun. And then delete this so we don't get as many errors. Yeah, it's
Wow.
64-bit.
It is.
I'm running a 64-bit architecture.
10 to the 19th. I can't. Let me count that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh yeah, it is. Like 20 digits. Big.
Let's count.
Like gazillions or something.
I think it's
100,000, 100 million,
quadrillions, as far as I
100
remember.
billion,
I mean, this
Trillion.
zeros is quadrillion.
quadrillions,
I don't remember.
septillion. No, I don't think it's septillion.
So we
What
have
is
names of
hundreds.
numbers.
Gosh.
Oh, how do I go back?
It should be quintillions, I think. Because it's 10 to the 19, or 1.8 times 10 to the 19.
Thousands, millions, billions, trillions, quadrillions,
Quadrillions, then
quintillions.
quintillions. Yeah.
Okay, so quintillions. It is. Okay. Maybe I was thinking of the. Oh no, it'll be like 9 quintillion, but yeah, big number.
Only 9 quintillion.
Yeah, only. It's too small. We have bigger numbers though. We have U128.
We need more.
Oh my god. To the 38. That's undecillions. Undecillions.
Oh my.
I'm not even going to spend the time to count that one out. No,
Yeah. Put it in the chat, I'll do it.
Okay, count it up. Enjoy. Yeah, I think we're good to end it here because I think this is a good ending point, and then for the next time we can go over ownership rules because we went over why we need ownership rules, and like why we even care about references versus just copying everything. So I think we are pretty set to go over ownership for the next time.
Let's go.
Yeah. And
Holy
I don't want to stay too long, of course.
I asked ChatGPT because I was not doing that homework. I put it in the chat.
Yeah, it's
340
340
undecillion.
Yeah.
Into the 36 power. Serious damn.
Yeah, just to end it off, anyone have any like final questions ending it out, or yeah, any final questions before I move on? Or we go into feedback?
No questions. I enjoyed
Nope.
this about specifically this book club meeting specifically about memory and the stack and the heap and how memory is allocated. It was really good to just go over it again because I know it's going to get more difficult in the future. So it was nice.
Yeah, in case you're scared, you don't typically have to think about the stack and the heap when you're actually coding Rust. It's just really good to know that there's a reason to it all.
Mm-hmm. I'm practicing leak code. I know it's not like incredibly important while doing it, but I always feel like more comfortable knowing what's going on while I'm doing it. So this helps a lot.
Nice. Yeah. Oh, and before I forget, there's no homework because we're just going to go over chapter 4. So finish chapter 4 if you didn't finish chapter 4, or maybe review ownership rules. And then for extra credit, if you did and you're interested in doing more, advent code is here almost. So try out an advent code problem in Rust and see how it goes.
I'm ready.
I think I'll do like a day or 2, maybe 3. I'll see how much time I end up with and how much I'm interested in going through it. I did one of an older year with good error handling and testing with Rust, and it was pretty fun.
Oh, jeez.
It was very nice to see how you can go because they didn't TypeScript. And then I ported my solution over to Rust, and I was very satisfied with the amount of different things you can do, like enums especially, because I was just using strings at the first part when I wasn't really thinking in like a Rust mindset.
Yeah, I need to go back to a couple years ago. I tried doing it in C and then stopped after like the first week. I need to go and like complete them.
We're gonna do some C next time, next book club. Spooky.
Next
Ooh.
book club. What's next
C or
book
C++?
club?
Just C.
Just C.
It won't be anything too deep, but we're just gonna see.
Rust if we were gonna have to do C++ anyway? Please no. I'm doing this so I don't have to ever look at C++.
We're gonna do C because we can type words on the screen and they will do undefined behavior for us instead of Rust, where we're just like, oh, I guess this doesn't work, so I can't show you running the code.
Yeah, I was gonna mention in my I have a demo in C of the undefined behavior.
I don't have anything too complicated in mind, but just running uninitialized data is interesting. And undefined. Yay.
Yep.
Okay. Since we're just to end it off, any more feedback? Like, did you like this going slower? Anything you'd want differently? Any suggestions for next time even? Anything you like seeing? Anything you didn't like? Anything you want to see more of?
It might be like just in general, I think a good idea to have a like stack / heap like thing drawn out already, like with labels, because it was sort of hard to follow like all the boxes when you were drawing them in Excalibur, like which ones you were talking about. It might be useful just to have like pre-labeled boxes or whatever you can move around. But yeah, I think it was good.
Mm-hmm. Yeah, I like the addition of Excalibur, helping to visualize like what you're talking about, what you're doing. Especially something like a diagram, like a stack or heap, that was really helpful and engaging.
Yeah, I figured it'd be more helpful than just saying words.
Just saying words. I haven't actually. I found a link to a cool GitHub project, RustViz. I haven't looked at it or tried it out yet, but it looks like it could be useful to try to demo some of the like borrowing stuff and like lifetimes when we get to it.
Yeah, I did hear about different. There's a different one that I heard about at RustConf that isn't RustViz, I'm pretty sure, but yeah, great point. We'll see if that's feasible. Anything else?
I guess a question about like the JavaScript visualizer. Like, this is unrelated to Rust, but does JavaScript actually allocate stuff like that on the stack? I assume it's kind of weird and does things differently since like everything's an object and all that.
Well, let
like
me tell you.
I assume it uses the stack strangely.
Everything is not an object.
Exactly, they lie.
It's
lied.
untrue.
What?
The memes are lying to you. So,
Oh, no.
Since we're getting into it, things like numbers are numbers. But when you want to call a method on those numbers, they use an object wrapper. So they're wrapped in a number object, and then that method is called on the value. But they are not objects themselves. So the number object would probably go in the heap. I'm not entirely sure, to be honest.
Well, yeah, but that's what I mean. Isn't that what people mean when they say everything's an object?
That's what they mean, but you still have stack allocated values like numbers. Doesn't change the fact they go on the stack. But also, to be fair, JavaScript spec does not specify what goes in the stack and goes in the heap. So it could do either one. Everything could be on the heap. You could do something different, whatever you want to do.
Weird.
Yeah,
but I mean,
it's very confusing.
But there's still like obviously everything, like the underlying data types, like integers and like characters, however they do the encoding. Like, yeah, they're their own types, but everything's an object because JavaScript wraps them in like an object so that you have those methods.
Oh, well, they aren't permanently wrapped in an object. It's a number until you call a method, and then it is wrapped in an object. And then that object wrapper is discarded.
Okay. I still think that counts as everything's an object, but that's fair, I guess.